I'm Colin Gray. I work for a company called TIBCO. TIBCO are a technology company. They've dealt in a lot of areas. But we've got a really strong partnership with the Mercedes team, and that's obviously the topic for today. But we've also got a lot of other sports things that I'll briefly mention. They might be of interest. So I think data science and sports in general is a really fun and interesting topic. I'll give you a little bit of background about who I am and how I got into this. I actually worked for the Scottish Environment Protection Agency for the last 8 years, where I was lead data scientist. And that was all around analytics and modelling of the environment. But in last June, I joined TIBCO. I'd been using TIBCO's software for 8 years at SEPA, and then I eventually joined them. And in week 2 of joining TIBCO, I knew they had a partnership with Mercedes F1 team. And then in week 2, they actually asked me to go to the Mercedes garage. So I was really pleased because I didn't know if I was going to get to work with Mercedes. I've been an F1 fan since 25, 30 years. So it's been very cool and a lot of fun to actually work with the team and help them get prepared for the season. Unfortunately, obviously, this season's been somewhat delayed, but hopefully we'll get racing pretty soon. So just usual disclaimer and confidentiality around what I'm going to show here today. But like I said, I don't want to cover too much around TIBCO as a company because we're interested in Formula One aspect of this. But you know, TIBCO covers these 3 areas. I'm in the predict area, so that's really where we do analytics and data science. But you can't get away from the other 2 big areas that we work with in TIBCO, which is connecting to lots of different data sources. You know, the amount of data in F1 is huge, and they're all in different places and different sources. So that's really important. Unify is all about how you bring them together. You can do things like virtualize data so that you're then ready to do predictions and machine learning on that. So I think as a data scientist, you can't avoid these areas. In fact, they're good to learn and embrace. And that's why we kind of cover all 3 of those when we're working with a team like Mercedes. I'm going to show you some of the tools that we actually use in sports data science and in the Mercedes team. You know, they're all about a big emphasis on collaboration, ease of use, quick production of machine learning models, low code, no code environments. You know, I'm going to touch on all those aspects and why we think they're important and how they bring a benefit. The 2 key ones are TIBCO Data Science, which is really the backbone of what we do. And it's a web-based collaborative tool. It works in database, so it uses things like Apache Spark and other technologies like that and Hadoop. The other thing we do have a big use of is just analytics, and we've got a tool called Spotfire. A lot of the Mercedes team use Spotfire, and we've got quite a few demonstrations of examples, and there's quite a few YouTube videos of the Mercedes team working with analytics through these types of tools. And the whole point is we integrate them all together and we embed data science in sort of visual analytic workflows. And that's a key part. You know, when you want to produce machine learning models and data science and get it out there, we get it used by a lot of people, you need to make sure it's clean and easy for everyone to use. You don't want it to produce barriers for people getting into your data science, and you want to be able to easily deploy models and run them. So one of the things that we have here is, as I said, it's mainly about Formula One we want to talk about today. TIBCO have been in a partnership with Mercedes for the past 3 seasons, and we obviously continued that partnership for this season. Obviously the season's not quite started, but we work through the off season where they're testing, helping things set up. And I'll take you through a few of those projects we're working with them. Obviously Mercedes and F1 teams, you know, the details of the projects and the data are quite guarded and secret, so I can't obviously give a lot of detail due to confidentiality, but I'll try and give as much of an overview and interest that I can. But we do work with other teams. You know, we've got interesting things. We've got a cycling team, a women's cycling team, where we help sort of analyse performance about, you know, the athletes and what they're doing there and trying to improve that. Another interesting use of data science and technology was we worked with an MMA fighter up here, and it was quite interesting because what they did was they put sensors all over his arms and legs and actually analysed how he punched and kicked and where the power was coming from and optimised his technique. So it's a really interesting field that you can sort of really get in-depth analysis of how to improve just the technique right down to one person's individual technique. And last but not least, we also work with the NFL, so American football. Roger Craig was a famous player from the San Francisco 49ers. And he works with TIBCO, and we actually helped use analytics to sort of show that he should be in the Hall of Fame, which is quite a fun project. This is just an example of what we did and how you can use data to sort of prove a point. Roger Craig was a running back for the San Francisco 49ers, if any of you are fans of the NFL. And he was in a team in the 80s that won, you know, the Super Bowl, the best, the whole point of the league many times, but yet he's not in the Hall of Fame yet. So we used some statistical analysis to prove that he should be in the Hall of Fame. So for instance, all these players on the bottom of this chart, and we derived a score of the performance based upon how well they played, you know, how much they ran, how much they scored. All these players are in the Hall of Fame. Roger Craig is the only player that isn't in this group, and you can clearly see he fits well in there, and these players here are those that aren't in it. So it's a good example of using analytics to sort of find key differences by merging stats and data. But we want to talk about F1 and what we've done here. So this is actually some pictures I took from when I was in the F1 garage. So Mercedes are down south near Silverstone, like many of the F1 teams in Britain. Here you can see this is Valtteri Bottas. He posted this just before the season was about to start when he was testing. You've got the TIBCO logo there. You know, we're obviously a partner of the team. They've got a really nice car just sitting in the reception. It's quite a cool reception to sit in. You know, when you get this is a car that was raced in Abu Dhabi in 2018 and all the trophies as well. And here we were actually talking to our simulation engineer explaining all the cars. So it's a really nice garage and environment to be in, very exciting. So a lot of the people we talk to, so one of them is, for instance, I work with is a person called Michael Sansoni, and he does a lot of simulations prepping for race weekends. And that's something we aid them with a lot. You know, there's an amazing amount of combinations before you get to a race. And every moment is different, you know, because of the weather, because of the car, because of the track. And it's very hard to predict and react to that. So that's something we work closely with them on. So that's really what Michael's talking about up here. So just some fun facts about Formula One. You know, the amount of data obviously is staggering. I don't think I quite grasped it until I was working with the team. They've got around 300 sensors in the car. What's interesting is they'll have more sensors on the car if they're not racing, but because sensors weigh something, even though they're very small, they will actually take sensors off the car for when they're racing and qualifying and then put them on for testing again. So you end up with different levels of data depending if they're racing or testing. They're getting 50,000 data points per second and about 400 gigs of data per race. And they've done a lot of racing beforehand they get there. So this is the types of projects we've done with them. I'll try and go in a little bit of detail on some of these. What we've worked with them is a variety of projects, and there's some we're actually doing right now that aren't on this yet. You know, things like wind tunnel optimization. So every part that you put through the wind tunnel, it's obviously very costly to run a wind tunnel, and then you've got to design the parts and put them through that wind tunnel. So one of the things we've done is actually look at, can you optimize and predict which parts will be better? You know, using simple models, could we predict that these parts are more likely to succeed before you even get to the wind tunnel, so that you only use the expensive wind tunnel time for the very best or very highest likelihood of success parts for your car? And so that's an interesting example where you can sort of really bring cost savings and time savings. So a lot of data science you do with in any industry is about predicting things and learning new things, but often just making things more efficient can be really important. And that's a really key point for F1, especially with all their cost savings and restrictions on number of engines, example. So that brings me neatly on another key thing that you can do for data science and Formula is reliability. For instance, a gearbox. Every time they change a gear, they record about 1,000 data points for that gearbox change, and they will change gear possibly around 100 times a lap. So that's a massive amount of data just for gear changes. And from that, and from analysis of that, you can optimize to get a very tiny millisecond in performance enhancement, and that's something that they've worked with us on. But that tiny performance enhancement can get you an extra place in qualifying, or even a few places. One of the things you can use that for is anomaly detection, for instance. So if you're watching patterns in real time of a gearbox or any part, if you start to detect errors or different patterns, you might theorize from that model. That model might say, okay, this part could be about to fail. You might want to switch it out before the failure happens. You know, if a failure happens mid-race or qualifying, it's a big disaster. But not even that. If you can detect a part before it fails, you can take it off, change it, or get more test time now. And obviously, Formula One teams are restricted to things like limited engines. I think it's 3 engines a year now, limited gearbox. So if you know something's looking anomalous, if you can retire the car early or even react to that somehow, tone the car down, turn the engine down to help protect a part before it fails, then you can possibly repair it or optimize it for the next race. One of the things that I'm going to demonstrate and is used a lot is visual analytics of car setup. The amount of attributes they have on the car and potential combinations is staggering. And they use a lot of nice dashboard and analytics produced through simulation and models to then pick that optimal setup. And that's something that I work with them on quite a lot as well. Race strategy, I think, is a very obvious place for data science, you know, predicting when the best lap time to pit, predicting what your opponents will do. But we've also worked on things like predicting the likelihood of being overtaken, you know, a lap or two in advance. You know, is your car showing signs of the driver and performance of the track showing signs that you could be vulnerable well in advance, and then you can react to it. And simulations is a big part. So these slides have got a lot of text on, and they're more sort of marketing of what we do with TIBCO. But I want with TIBCO working with Mercedes. But I wanted to just highlight them because we're covering kind of 2 of the key things that I'd like to show off today in the demonstration I've got. You know, Mercedes really are looking at masses of data. So being able to sift through the mounds of setups that they've got. So they run simulations before every race. And they run simulations based upon previous races, but when you get to the track, it's completely different each time. You know, if you go to a track even an hour or 2 apart, it will react differently, the car will react differently. So they run masses of simulations and produce all sorts of charts, looking at regression lines, looking at attributes, predicting where and what will be the optimal setup for your car. And it's quite interesting because sometimes what will be fast in one part of the track will not be fast in another part. So how do you get that balance of, you know, if you're setting up things like the pressure on your suspension, things around the angles of different wings, engine setup, and they won't all work throughout the same lap. Within one lap, they could be optimal and not optimal multiple times. So it's all about finding that balance in amongst these thousands or millions of combinations. And that's a really interesting and fun challenge. But what's interesting about it as well is it's done in such a fast pace. I think if anybody on this meetup works in data science, a lot of the industries we work in, the pace might be over a week or 2, or you might be looking at information over a month or a year in modeling. In Formula One, you're doing it over a very short time frame. It could be hours or a couple of days. And then it's over once the race is gone and you move on. It's almost like you throw it away slightly. So it's a very interesting, different challenge because you have to do things at a very high pace. So another key example that, again, I'm going to show a little demonstration of a sort of our own version of it is digital twins. And digital twins is a thing where what you're actually trying to do is mimic something that's a real life situation or a real life thing that's happening, and you try and mimic that using digital twins. So you try to make a sort of digital version of it. And that's a huge thing for sports in general, but for Formula One, of course, if you can mimic the car's behavior or a driver's behavior, you can run simulations around that and optimize it. And so this is a really big part of what they do, you know, running simulation after simulation to try and predict what is the likelihood of what will happen, you know, with their own cars, with other cars, and then try and pick the most likely place that they're going to do well. So it's quite interesting because I was looking at this talk today, and Mercedes actually posted On Facebook, I put the link here. I can put these on the chat or on the Meetup page for you afterwards. But they posted a video showing off their own simulator. And here, so this is just a screenshot from the video that you can look at on Facebook. And you can see the simulator here. They've got a lot of screens. They're using a lot of time series data and dashboards and streaming live from the car to their systems here. So during the race, they would be doing this constantly as well. They've got, you know, a whole team at the track and off track, and they're streaming data constantly about the car. And here you can see like the types of things they're doing, where they'll be comparing laps. There'll be 2 laps there, the blue and red, looking for fraction or tiny differences, which might explain why one lap was faster than another, why one setup works better than another. And obviously, these simulators cost hundreds of thousands to run, and they're very expensive, but they bring so much gain for the team. So this is a very powerful example of a digital twin, and possibly an extreme one, because they actually have the car there, a sort of the full car, and they use that to sort of run the simulator. So at this point, I'm going to actually show some of the stuff we do that's a sort of mimic of the Formula One, and because we've got our very own simulator. But at that, and what I'm going to do is show the data we collect through our own TIBCO F1 simulator. Obviously, we can't have a very expensive Mercedes type simulator in the same way that they do, but we've got our own one to sort of mimic and that we can show off. And the good thing about it is we can use the data for that to show how you can use analytics, and it's the same way we model and do that with Mercedes. So just pause there a little bit and just see if everybody's got any questions before I go on to this sort of more in-depth analytics demo and data science demo.
A few questions in, Colin, for you.
Okay.
Let's go to the first one here. Are anomalies usually further investigated if they had to compromise performance to understand why the readings were like that?
Yeah, so you know, there's a lot of ways of detecting anomalies as well. You know, you can use a neural network, for instance, to detect when things just look different without ever knowing why or what is different, or more described models that know what they're looking for. But yeah, what you would then do is they've got simulations, you know, in Formula One, they will store data for previous seasons, for previous runs, for previous setups. And what you can then do is relate that back to try and understand what caused that. You know, was it unique to the track? Was it unique to something that happened? Maybe they rode a curb too heavy, or was it just that the part is just degrading? So there could be a lot of reasons, and so that you would then try and delve into the data and find that out. You know, so because if you learn why, obviously then you can prevent it in theory next time.
Cool. A bit of a cheeky one here from Garrett. Before you joined TIBCO, which F1 team were you a fan of? And if it wasn't Mercedes, have you admitted it to them?
No, I haven't. No. It's funny. I kind of switch my allegiances. It often depend on the drivers. I think sometimes you follow drivers more than anyone. I loved Schumacher. So, and when he came back to join Mercedes, I thought it was brilliant. And I always, you've always got a small leaning sometimes towards people, you know, if there's someone Scottish racing, so like Paul di Resta and things like that. So no, I've always liked the Mercedes team. I think it's very good, and obviously I support them full-heartedly now.
Obviously, a few more. Let's take one or two. What sort of lap time benefit could you attribute to your data science overall?
That's I mean that's quite a difficult question. That's a question I've had in many industries. So I've had that question when I worked in pharmaceuticals. When you try and pinpoint, the difficulty with answering a question like that is when you try and pinpoint an individual change, a change to one thing, like say a model you use, I think that can be quite hard to pinpoint because there's so many things at play. But the gearbox example, so when they were able to visualize the gearbox is better and look at all those changes, they did get a very small gain through those improved visual analytics and models, and that was able to translate into, you know, a millisecond or so for a lap, and that so they know that gain came from changing the way they looked at the data. And Another thing with the wind tunnel example, there was a very small percentage increase of, if I'm remembering right, of how it predicted the optimal parts. But that equates, and that was just from changing the model we used, but that equates to a lot of time, money, and performance that leads on from that. So I think it's hard to always measure these exactly, but you're looking for, you know, changes that have an impact.
So there's two more, and this one's interesting. Being someone who doesn't know a whole lot about F1, I know the rules are kind of under scrutiny a lot. So there's a question here about the rules, and if you could change anything about the rules to help data science make a bigger impact, what would it be?
Oh, that's an interesting question. Right now, it would be that I'm allowed to work in F1 because the FIA shutdown applies to us, even though just as partners of Mercedes, so we can't even work on TIBCO. TIBCO can't even do a lot of these things around performance for the shutdown. But that's a tough one, actually. I guess in some ways, when teams, this is a general thing for companies, you know, even in an industry, where teams have so much intellectual property and ideas and they're racing against each other, they obviously aren't, there isn't a lot of sharing going on. I wonder if there was a way to access multiple teams' data. You know, I think that's true of any industry, pharmaceuticals, even if companies could access each other's data better, you would get a lot more gains. So I think that would be an interesting one, because we can only look at Mercedes, but imagine you had Ferrari, Williams, and the rest. You get a much more varied and much more rich data set.
Okay, there's one more, so we'll just do one more.
Okay,
Oh, there's another one after coming in.
Yeah, we can put that at the end as well.
Let's see. Are all the predictive data or analysis communicated to the driver as strategy in real time, or is the race strategy mainly up to the driver?
So, I mean, I'm not an expert in the race strategy, but I do know. So what's happening when they're racing, there's obviously real-time data coming off the car. What's interesting is that real-time data is not as extensive as when the car comes in. They actually download data from the car when it comes in, and they get a much bigger bulk of data, and then they can do richer models. So they will have people running models and real-time strategy that they are predicting for the driver. So it'll be a mixture of they will have things that their models and data tell them, but you know, I'm guessing, I've never asked the drivers, haven't been lucky enough to meet them yet, but you see it on the TV that they can make a decision, or they could say something's changed in the car, or I don't think this, or I want to stay out. So I think the most important thing for data science to me, and I think this is really key, it doesn't matter in industry, is the collaborative nature of data scientists. The data scientists can do work, but you must also get a real great input from the domain experts. And the domain experts may not understand data science or analytics, but they know their domain, you know, and I think in that case, it's the driver. So you've always got to respect their thought as well, regardless of what the data says.
Cool. Right, so do you want to jump back in, and then we'll get to Adam and Zach's questions at the end. And if anyone else has questions, by the way, just leave them there and we'll get to them towards the end. Cool, thanks, Colin.
No props. So, like I said, obviously, I can't show you Mercedes real data, but what we do at TIBCO, and it's a lot of fun, but it's also quite informative, and it's a good example of technology and data science, is we run at events. If you ever see us at an event, we will be running, hopefully, if you're lucky, the simulator. So this is our own version of a simulator, and this was run at the Big Data London event last November. And we did this with some people from the Mercedes team. So we actually had the Mercedes car. Here you can see a screen, and it's running the F1 2019 computer game. So I'll just show you the video to give you an idea of how this looks in real time. So you can see he's racing the track, and you're sitting in the car. This is a real car. And then what we're doing, if you remember the screenshot before of the real simulator at Mercedes Garage, we're also running in real time our own simulator dashboards. So we have various attributes here. So the speed, delta to the best lap, steering angle, gears, brake, and the track position, damage and heat of tires, etc. Even the mimicked or modeled G-forces a person experiences. But one of the things we do, and we added to this, was a predictive element. So, and that's what I'm going to show off today in the demo, is how we build predictive models. we were actually trying to predict someone's lap time up here before they finished the lap. Now, that's quite difficult from the beginning of the lap because there's so many combinations of what could happen in terms of driving. So if I just let that run, what you'll see is that time gradually changes. And that's the model constantly running in real time as it gets new data in real time from the car. So as this person's driving, that is streaming data in real time to our technology, and then we're trying to run these data science models. So that's what I'm going to show you, is how we built those models and how they learned, or did they learn through the process, and try and delve into a bit of the data science and the data you get. So a little bit about how this works. You know, this really, my area, again, I've said, is in the data science, but there's a lot of interesting technology going on, and it's the type of thing that, you know, any industry who wants to work in real time, like Formula One does, needs to enable. We've got the game, the F1 29 game, the official game. It's the same one used by esports, if any of these are esports fans. What that has the ability is to stream out telemetry data, and it goes into this technology that's an open source technology called Flogo. It's an edge, so, you know, a sensor edge computing language, very optimized for real-time data. And then we put it into our own streaming tool. And what that does is it streams the data, it runs models, it does aggregations, splits the data, and it will run in real time a model. So what happens is that then goes out into Spotfire. So the dashboard you saw before was a Spotfire dashboard. So it's getting fed real-time data. Every second it gets an update from the person racing. But it's simultaneously we're storing the data in a Postgres database. And that's so we can do historical analysis. But it also allows us to then put the data as people race into our models, rebuild them and deploy them in real time into the streaming engine again. So this is quite a realistic scenario that you could do at, you know, an F1 race or in testing, is you could be deploying new models or new configs out to a system or something in real time. So we've actually done this where we've deployed a new model as the person was halfway through the lap, and the model changed in real time and started producing new predictions. So, I mean, it's quite fun to talk about the game. You know, it used to be that computer games were so basic, they didn't really have real world applications, but, you know, esports is a huge business now, you know, big money, 5.5 million viewers last year. But what's kind of interesting is people are up and coming drivers are actually starting to go into the esports series where they race this F1 2019 game. You know, and for the first time ever, an esports finalist has joined the Formula 3 grid as well. So it's an interesting crossover between, you know, computer games or what seemed like computer games and real world. So now I'll go and show you what we did. And I want to try and show this as a high level of lessons we learn as we do data science in general, but also how we apply that to the domain, which is Formula One. So we set ourselves a challenge of, we want to predict the final lap time of someone racing. So people, as you saw, would come to our event and they would race in that car. And obviously these are just random people who've come to the event, you know, could be any of us on this call. And the variables or the variability of skills is somewhat large, shall I say. And it's there's a lot of kind of fast people and there's a lot of people who just go crazy and end up spinning off. So it was quite an interesting challenge because of the different variety of drivers you have, whereas in F1, obviously they're very consistent. And that led us to the idea of, could we even predict a crash? So what we thought was, could we use data science to predict when someone's driving erratically or in a way that leads up to a crash? And that could have some interesting real world applications. You know, there's also a lot of technology and data science in cars now. But before you do any data science challenge, you know, you've got to have a think about what limitations or what things you might need to take into account. One of the challenges we had was we didn't really have data to train before we went to that event. So we didn't have a lot of information to teach the model how to predict before the event started. So we ended up having to generate our own data. It's a tough job, but I had to do that. I had to get the pedals and steering wheel at my house and race the track over and over myself to train the model. So that was quite fun. Another interesting thing about Formula One is when you're predicting something, the standard of accuracy is so much higher. I could predict something within 2 seconds, And that might be really, really accurate for a process that isn't Formula One, but in Formula One, 2 seconds is huge. So you needed to have this accuracy. And one of the things you must always keep in mind with data science is if you're going to go into production, in my career, I've seen a lot of times data science doesn't make it to production, i.e. they don't use it for real business use. You've got to take into account all the different technologies and data and things that are involved, you know, and that means you might make compromises, and you might have to not go with the optimal model, but you need to do that to go to production. So a little bit about the data. This is the data that comes out the F1 2019 game. There's a lot of data. It's got about 131 columns. It outputs 10 rows of that 131 per second. So for instance, a lap of the Brazil circuit, and all the demonstrations I'm going to give today are from the Brazil circuit. That's about 105,000 data points per lap. And you get things about track and position, you know, where they are on the track, but it's not just, you know, I don't mean literally just here, it's literally to a very highly accurate coordinate of where exactly they are on the track. You get all sorts of information about, you know, their angle, their speed, their velocity, their local velocity. You also get things about tire, brake, suspension, you know, heat, the loads being put into them, and it's per tire and per suspension. So you get 4 readings for everything because you get 4 tires, 4 sets of suspension. But you also get interesting attributes about the way they're driving. You know, have they damaged the car, the G-force being experienced, and the types of speeds, how they come on and off, the acceleration or the steering angles they use. So there's a massive wealth of data. So it's a really good fun and interesting challenge to use that. So just to summarize, this is the process we went through to build models for our own simulator that I was showing you there. It's a standard process for every data science task, I think, gathering data, exploring it, cleaning it up, handling the issues you find, generating features that you think will let you predict things, trying out some models, optimizing them, and operationalizing those models, getting into production so people use it. But the reality is, you think it's a linear process, but you constantly hop back and forth as you learn things, jumping through stages. So it actually becomes like, you know, and there should be multiple hops forward as well. It really is a very iterative process. So I think, you know, data science is really an evolutionary process. It will constantly evolve and change, and sometimes you will go back many steps, but to get forward to a better place. So I'm going to come out of this and introduce you to some of the technologies we used and run some of these in real time. We use this web-based tool called TIBCO Data Science, and in here you can have various projects. So this is like my workspace with lots of different projects. And it's a very collaborative tool, so the idea is lots of people work on it, and I think that's a really important thing for data science. So for instance, I've got my F1 simulator project, and here you can see there's a whole suite of different people who work on that. And we can have things like what data is in here, what data sources we've got. So you get different things like Postgres and Cloudera, Hadoop, etc. And you can run all sorts of things. But the nice thing is you can store all your files. So I've even got the presentation I've been showing you here. I've got some Python notebooks in here that people can collaborate on and tag and things like that. We've got some workflows that I'll show you that actually do the data science. And we've got Spotfire tools to, like I said, that's our visual analytics tool. So what we want to do is we're going to show off doing some analysis before we even try to model. So I'm going to open this tool, the lap analysis tool. And this is just one way of looking at data for Formula One. You know, this is showing us information that we recorded from real laps done at that event. So that same video I showed you earlier, this is all the laps plotted on the track for that people raced in London for those 2 days we were there. So if you zoom right in to give you an idea of that, it may be a little bit hard to see on the detail, but if you see the tiny dots there, every dot there is one single data point from a lap that somebody raced. You know, and you can click on that and get information on what they were doing there. So there's like 131 different attributes for that single point, and they are recorded every second as you race through your lap. So what we've done here is like show how you can use analytics to learn how to drive without even getting in a car. So what we've done is we've used the color scheme. And I'll use this consistently throughout the analytics. Where it's a sort of pink or purple, that means it's the fastest data point, or it's the biggest number, you know, because when you're going purple in Formula One, that means you're going the fastest. So what we did was we coloured all the best points on the lap by purple, going to green for sort of near the best but not the best, and then down to sort of greys or blues for when you're going quite slow. And you can see quite clearly straight away, just from plotting this on the track, you can learn instantly, if you know nothing about this track, you can learn instantly how to take the corners. So this is a start point of the Interlagos Circus in Brazil. You start here and you race down to this very famous chicane. And you can see the people who are purple, there's a very strong line that they take. And then all the rest who do lap times not quite as fast are all sort of scattered around that. You have some interesting ones where some people have got away with going off track and still done very good laps, but in general, you can see a really strong line. So we know how to drive that corner before we've even got in a car. So what I want to do is take you through an example of that, so take that to a sort of a different level. So let's look at one corner of this circuit. So here we are. So every F1 track split into 3 sectors, and this is at the end, the start of sector 3. So what happens here is they're driving in here and they're going around this left-hander, and then they've raced this really sort of looping, almost straight but slightly curved approach to the finish line. So it's a really important part of the track. So what I've done here is I've highlighted the straight before this corner. And what we can see here is the difference in people's attributes. So along the top here is the final lap time each person did. So this is where people finished their lap in around 70, 75 seconds, 75 to 80, 105, 110. So the fastest drivers on the left, the slowest on the right. And just by looking at simple attributes, we can learn something about driving already. So what you can see is the fastest drivers are carrying the most speed at this section on the straight. That's what you would guess. But what's interesting is they're braking the hardest by a long way. So there's 74% brake, 65% brake, whereas the people who produce slow laps, who are slower drivers, they're barely braking. So not only are they carrying more speed, but they're heavily braking. It might almost seem counterintuitive. So if we then move into the corner and see if there's a big difference between fast and slow again. So I'm just going to highlight the entry of the corner. And here you can see, again, the purple is the best. And this graph here is actually just the speed. So pink means higher speed. And this one is brake, so pink means applying more brake. So we can see sort of different heats maps, if you like, across the track. But now we're in the corner. What we see is the speed that everyone's doing is actually about the same. So everyone ends up in the start of the corner roughly the same speed, despite the fact there was a big difference in the straight before. But now you can see the slow drivers are braking more. They're about 40, 38%, whereas the fast drivers, they're not applying so much brake. But another interesting thing you might see is steering angle. So this is the percentage they're turning the wheel. 100% is, you know, the full lock of the wheel to the left if it's minus, positive if it's right. The fastest drivers have got quite a strong angle to the left, minus 40%, minus 35. And what's interesting there is the very fastest is minus 40, but everyone else is about 35, 37. So for instance, that tells us that if you want to get from being quite quick to the best, you've got to look at your steering angles. They're able to steer in harder into that corner while braking less. So again, braking is a big factor. So then if we come to the corner exit, so when you come out the exit, you want to straighten the wheel up, you want to hit the accelerator as hard as possible. So again, we can look at the difference here. And you can see a huge speed difference between the best and slowest drivers. The throttle for the fastest drivers, they're almost at 100% acceleration at this point, but they're still in the corner, but they're able to accelerate hard. And you can see the steering angle for the very best people is much less steep than for the slower drivers who are still steering hard and still braking actually. You can see there's some lines here as well where people have gone completely wacky and you know, lost control and spun the car. So you get some really interesting driving lines taken out as well. But that's just a very simple one way of looking at the data. You know, there's so many stats, and it's just to show how we can use analytics and geoanalytics to learn how to drive without even getting into a car and optimize for a track and a circuit. But what we wanted to do are predictions. So we really want to be able to model how each person races. So the first thing we need to do then is get do some feature selection. So in feature selection, what we do is we're looking at what of those attributes or variables that come out the car when they're doing their lap can we use to predict how they'll, what lap time they'll do at the end. You know, and this on the left, this is the full suite of attributes that comes out the game. It's amazingly similar to the types of attributes that come out a real F1 car. You know, the accuracy of these games is quite incredible now. And what we can do is if we click on speed, we're plotting different patterns of speed across the lap. So here's the start of the lap, here's the end. And what we're trying to do is we can't predict on a single data point because it's too granular. So what we take is a rolling 3-second average. So this is the 3-second average we're plotting of all the recorded times and data as someone raced a lap. And this is all the laps together of everyone. And here we've got cumulative sums just in a different way. And what we can see, we can use a box plot, for instance, again with the fast people on the left, the slowest on the right. If we highlight this, we can see the pattern. So the purple again is the fast lap. So you can see that generally faster people maintain a faster speed as you might expect throughout the track than say down here in the bottom. We highlight that, it highlights the sort of grey lower thing. But you can also see that the variation, the spread of speeds, fast drivers tend to keep a more consistent speed, whereas there's a much greater variation in speed. So you could click through lots of different attributes. We can look at engine RPM. Okay, what you try to see is there a good distinction between purple and white? Engine RPM, okay, that's a bit like speed. We can look at inner temperature of the tires. There is a pattern, but it's harder to see. Tire wear, for instance, I mean, that's not going to tell us anything. So if we want to model these, you really need a better way. You don't want to manually go through these one by one. You know, something like that's very hard to tell if it's a good indicator for modeling of speed for lap time. So what we're going to do is bring in some real data science and use a machine learning model to tell us what's the most important features of a track. So what we do for that is we can build a workflow in this tool. So I'm going to show you a workflow and how that actually operates. Just give that a second to open. So this is a workflow that we've built and used to generate what features might be the best to predict. And what it's doing is it's reading data here. It's all web-based, but this is taking data from Postgres. And you can simply just drag and drop everything. So it's a low code, and you don't need to write code to do this. Anyone can do it. You can join data. So I could just say, right, and click on that and show me the results of the join. And it shows me all the data that's come out from that join. You can see all the data here. And you can just right click and run on anything and just say, you know, run to here. And it'll actually start building all that for you. So here at the end, we've got these models. And what we're doing here is we're actually using a forest regression, a random forest, to tell us what's the most important features. So if I run this, it's going to take all my data from track. So you can see it's going to read the data, it's going to join it all, put it in Hadoop, generate features, and then run the model. Now I had pre-run that, so that's why it's so fast, but if I cancel that and run it again, it'll actually run that model in real time and produce a prediction of what's the most important features for each sector in the track. So we can build these workflows here, and that's great, but you know, you might want to let other people run this kind of model features thing. So what we can do is actually hook that workflow into our Spotfire tool and configure it from here. So you can pick any track, you can say how many laps you want to analyze. So I could say I want to analyze 100 laps from Brazil, and I want you to build 15 random trees. And when I click model importance, it actually sends, it crashed, that's ironic. It sends that job to that workflow with all those parameters. It probably crashed because I was running there. Let's try that again. Yeah, so now it's running, and it will then post the results from this workflow into our dashboard. So here you can see, like for sector 1, it's pulled out information like engine temperature or different things like lap distance or coordinates. And that's quite different from what we might have picked as a human, because it can find relationships that we don't see. So once we've picked our features, we want to actually build some models. So we have another workflow that does a very similar work process where you're hooking all your data together, calculating features. But this one, we're going to build a series of models. And what's nice about this is you can just drag and drop a model. So if I wanted to put in a random forest, I can just drag that on. and build a random forest for that model now. And you can configure all these, you know, there's all sorts of hyperparameters you can do. So when you do data science, you know, there's a lot of ways to do this. Now, but one of the nice things is you don't have to be stuck to drag and drop nodes. You want to embrace people who can write Python and R. So you can actually have Python notebooks as well. So we wrote a Keras neural net model for each sector. And here you can see the code. So we're mixing and matching, you know, custom written models with sort of pre-built drag and drop models. So eventually we ran all these models and got results for every sector, and we want to see which model was best at predicting lap time, and then how much they learned. So I'm just going to show you this, the actual output from these models, and how we learned how to predict even more than we realized just from the data from the game. So we had some training data that's here, and we had some test data. So the test data was real laps from the second day of the event, just to prove which models were best, and the data we trained it on. I'm just going to actually close that down so we don't have to see it. Just get that off the screen. There we go. So what we run was the models for each sector. We would predict the final lap time. So here's your linear regression model that I did, the boosted trees and the neural network from Python and using Keras. And we've got our R-squareds here. So each point here, this is the predicted time to complete the lap. This is the real one on the x-axis. So you can see the R-squareds aren't very good for this sector 1. That's probably what you would expect. You don't know a lot about the lap yet. Lots can happen. Sector 2, it's getting a bit better. Sector 3, it's getting a lot better. But you can see the boosted trees generally has a higher R-squared, so we're thinking it's probably the best model. And then you can look at the residuals that came out of the model, i.e. the difference between the real value and the predicted value. So if it averages around 0, you know, it's a good thing. It's averaging around the right prediction. So we did this for all the models in first pass, and we decided just to train the boosted trees for the models throughout the event. We could mix and match, that's a nice thing. We could mix and match and use linear regression for sector 2, boosted trees for sector 3, but for simplicity, we just went with boosted trees. So one of the key things we wanted to ask was, will the models learn? So we were rebuilding these models in real time. So the data here is from before the event, how the models performed with our test data. And then the data here is how they performed after 1 day of the event. You know, so they've got a lot more laps to learn. So you can see that R-squareds jumped up a reasonable amount. So we can see in the average residuals now on 0, where it's 1.5 before. So we can tell, 1, the models are learning and they're predicting reasonably well. But one of the most important things about data science, and I mentioned it earlier, and particularly about when you're working with Formula One, is you've got to put domain knowledge into it. R-squareds are okay, but they hide the truth of what your modeling is doing. So what you want to do is plot models on the track and assess how they're performing in a Formula One context. So what I've got here is I'm going to look at 4 example laps quickly. And what we've got is, this is the predictions of 2 different models throughout these laps that people raced at the Big Data London event. So the dark blue model is the model that was trained with the extra data after a day of the event. The light blue was the original model with only the pre-event data. And here you can see the original model struggles on this lap. It's overestimating, it's predicting a much slower lap, because this is the residual on the axis here. So it's predicting about 10 seconds slower than what the person really did. Whereas the new model with extra data, you see it performs much better. It's around the perfect prediction of 0, i.e. difference of 0 seconds from the prediction. So if we delve into this though, it's quite interesting. If you looked at this model and you took this section here, you would say this model is really poor. Its R-squared would be awful. Its residuals like -10, -12. So it's saying it's 12 seconds off the real lap time. So the final lap time is 96 seconds. But when you put it in the context of the track, it becomes, actually you realize the model's really quite clever and doing more than you think. So the red points highlighted are where a driver made a mistake, and we've derived that from information coming off the car. So here you see the model predictions jumped up before a mistake happened. So it starts to jump up here because it anticipated a mistake, and it's around here, so the person touched the grass. But then there's a really big jump in prediction, so it's predicting a much slower lap here. It starts to predict a much slower lap. And you can see there's a big mistake here. So if I highlight that section and see what happened. So what happened is, before the accident happened, that predicts that something was going wrong. And then you can see the person went skidded off, hit the wall, and the X's there meant they damaged the front wing of the car. So the model was able to detect they were going into that corner too fast, which meant they wouldn't be able to turn. And what actually happened is they cooked the corner and spun into the wall. And then the models sort of work out, okay, they've lost their wing, and they sort of settle down again. But what happens is, because they've lost the wing, they then can't go around the corner, and you get this other anticipated spike by the model. So it's really interesting. We didn't expect that, but the models can actually determine before it happens that someone's in the bad position and the wrong spot on the track, they're going too fast, or they're not braking the right spot, or they're about to have an accident. And that's not something we expected. So it just shows it's really important, because you might dismiss these models as being poor had you just looked at simple stats like R² and things. But actually it's being a lot more clever than you think, because who knows what the lap time would have been here if they hadn't had those mistakes. So I will just jump out and back to this. I'm conscious of the time as well. So we did expand upon that idea of the crashing, and we started to predict whether there was a likelihood of some damage or severe damage, and plot that in real time again as they drove through the track, and that was quite an interesting project. So I'll just stop there, because like I say, I'm conscious of time. I appreciate you all listening and staying online for this. And we've got a lot of content. You feel free to contact me as well, and this is my Twitter handle. If you want to learn more about these tools, you can go to the TIBCO site. We've got a community site with items you can download, and a wiki and spot fire trials and things. So, and we also run like data science that are very generic. It's about helping with data science in general. Things like Dr. Spotfire and Dr. Data Science. So, there's lots of ways to keep in touch. So thank you very much.
Thank you, Colin. Now is when we all clap, but we can't do that.
Yeah.
So,
Yeah.
But I'll give you a clap from everyone.
Yeah,
so well done, Colin. That was great. That was fascinating. That was really good. Suppose we get back into the questions, or we'll be here all night.
Yeah.
So from earlier, Adam was asking, do all the teams have a partner similar to TIBCO, and is the data they produce shared with FOM? Also, why, in your opinion, are F1 insights powered by AWS often incorrect?
So yes, there's lots of partners. There's a lot of companies work with different teams, and you'll see that. One of the people we work with, actually a customer we work with called Vestas, their wind farm, they work with the esports, the Formula E Mercedes team. But I know there's other teams like Red Bull and Williams. They all have technology partners. It's because there's too much for one team to do in itself. You need to reach out and build partnerships, and that's really key, because there's so much to learn and do in F1, and they've got lots of expertise in F1. Do they have all the expertise in connecting data, unifying it, predicting it? They might do, they might not. So you bring in partnerships and then work together as a collaboration. So you will find a lot of teams have different collaborations around that type of thing. So the second part was on the data, or FIA, was it?
Is the data they produce shared with FOM, and then also about the AWS insights being incorrect?
I don't know what you mean by FOM. I'm not sure about that.
Adam, if you're still here, do you want to jump in? I don't know if he still might have.
I don't know, it might have still.
That might not be so.
Nah, it doesn't matter. I could guess it's FIA. I mean, I don't know. I don't actually know about the data sharing, I'll be honest, of what's done between the team. I presume you have to submit data to the FIA for scrutiny. But
Formula One management is what Adam has said.
Oh, right, okay, yeah. I don't know for sure, but I would imagine you have to share some of the data. Yeah. AWS Insights, I can't say how their models work. I think the insights I've seen that AWS do are sort of during the race, sort of to give you some visuals of the race happening, but it all depends what they're training it on. They maybe don't have great data if you think they're not predicting very well. So I don't know what they're using for that, or the detail.
Cool. So we've a question from Zach, who I can see here on video as well. Just jump in if I don't kind of explain the question properly as well. Do you think that there's a particular bias either towards collecting the data from either the vehicle or driver channels?
Could you explain what you mean with that? I don't know if he's can unmute or explain it.
There he is.
When sort of like during a lap, there's a lot of data collected from the driver's side. So sort of great example would be steering input. Or is there more of a bias like the vehicle size, like suspension travel or engine temps? Is there more sort of a bias that you find softwares or yourselves tend to look at more?
Oh yeah, no, I get what you mean. Yeah, so basically, you've got a lot of information that the driver's effectively producing, the data they produce from the way they steer, the way they brake, versus the car's data. I don't know if there would be a bias, because I guess it depends on what your use case is. It's what you're looking at. I mean, if the driver wants to learn why somebody's gone faster around the corner or something like that, I guess you would compare laps. So you'll see, like in their simulator where you compare laps, they'll look at very detailed attributes of steering and braking and all those things, and then could see a tiny difference for one corner. Oh, they broke 10 meters later than me, or they were steering slightly different. But if you want to optimize the car in general, you know, for any driver, I mean, obviously you have to take into driver's style and ability, but you could optimize the car generally for a good suspension load, you know, the pressure you put in each spring, and tweak that throughout the race. So you would do both. It's dependent on what you're trying to tackle at that one time.
Have you come into any issues in the past, Colin, with changing drivers and stuff like that?
I mean, I've not been, because I've only been working since June, and it's really only the tail end of last season. Yeah, I mean, I haven't got personal experience of it. I know when you talk to the team and stuff, you know, the driver obviously plays a huge part. So they do change setups, and they do model each driver individually. So if you imagine all the combinations of the car, you then double that, because because you've got two different drivers. So that is something they do take into account. Each driver's different, and the driver's way different, and I guess they probably set up the car different as well for their own style. So
let's see, next question. So for Craig, going back to the simulator, Craig is wondering, you showed the prediction of the lap being constantly updated. Can you elaborate on the implementation of this? Is this a neural net under the hood or something else?
So that was what I actually was demoing at the end there. So the one that was running in real time that I showed you in the video of our event with our simulator, that was a gradient boosted tree. We've tried random forests, we've tried neural nets, we've tried linear regressions, and we've tried optimizing around those. And we've done it at different tracks. So we've run lots of events. We've done it in Brazil, Abu Dhabi, Silverstone, Austin, so circuits of America. Sometimes a different track will suit a different model, but in general, I find gradient boosted trees are very solid. They're very reliable. Sometimes a neural net will pull out a really weird answer that's way off. Boosted trees tend to be a little bit more, or I just find tree-based models a little bit more consistent. So that's why we've stuck with the boosted trees for now. But it's something you constantly iterate and test, you know, to optimize.
So Steph is wondering, are data scientists required to attend races to explain these things to the team? Is there a natural language generation element that does that for you?
That's two interesting concepts. So in Formula One, I believe they have a limit of how many people they can take to the track. So what you have, and certainly in the big teams like Mercedes, is you have a command center at base. You know, where there'll be people sitting streaming the data from the track to where they are. You know, that'll be near Silverstone or in England for a lot of the teams. So you have a suite of two teams working together on track, and then still at the garage, and they'll be seeing all the same information, but working in different ways. So I guess it's up to the teams who they prioritize to take. You know, I know that, for instance, one of the people I was mentioning there, the quote was from, about this, who looks at the simulation and setup, they tend to go to the tracks because they're constantly reacting to changes on the track and advising how to set up the car, whereas they might have other people stay at the garage. And there was a second part, which I forgot again.
Or is there a natural language generation element?
Oh, yeah.
Does that for you?
I don't know if people use natural language generation. What they do, it's a good idea and it's an interesting idea. It's something we've looked at TIBCO. Actually, we've used it for even analysing and working with data for the COVID situation, where we're trying to convert stats that have complex statistics behind them into language that anyone can read and act upon. So it's an interesting one, because what people do is they take all this data and then they present it to various people to try and understand. And those people might be high up managers down to technical engineers. So how do you pitch that? And that's true of any data science task or analytics task for any company. How do you pitch it so lots of people understand it? So natural language is a good idea and a nice way to do that if you can't be there in person, because you might not be available to explain it, or you might not have time. So having someone that interprets it so that everyone can react to it would be a really good idea.
Cool. And there's one more from Andy. It's kind of more general data science question. Last week, one of the speakers reckoned that data science projects had around 15% success rate. Is that consistent with your experience? And if so, why?
I don't know about percentages. You know, in my career, I've worked in a few different industries. The biggest problem I see with data science, and maybe that's reflective of 15%, is there seems to be a lot of data science projects don't make it to production. They often stay at a data scientist's desk or an interesting concept. I think there's a lot of reasons for that. One of the things I think is that they're not always focused on a very well understood business outcome. It's very easy to play with analytics and data science, and it's lots of fun and interesting. But one of the most important things I would say to any data scientist is keep focusing on the key, one or two key business use cases you're trying to achieve, and don't let yourself get too distracted. And that's what I meant about making compromises with technology. There was lots of things we could do, but we understood there was limitations to certain data and certain technology. So we couldn't do the perfect data science model, but to get to production, we had to do it in one way. And those models we deployed at the events with our simulator, we built the first ones in a week. So they weren't optimal, they weren't brilliant, but they were good enough. And they did the job we wanted them to do. So I think that's the problem, is that there's a lack of experience, because it's quite a new field, of how to get things to production. And I think we can learn from other, even IT type roles, more development roles, of how they do that. Because you have to be quite focused and be quite disciplined to keep pushing for that objective. So I don't know about 15%, but I wouldn't be surprised if it was something like that.
If anyone else has a question, please get them in now. That's the last one in the chat at the minute. Just give another minute to see. But thanks a million, Colin, for getting on and doing this.
I hope it was interesting to people, and it's a real shame I couldn't come in person. Like I said, it would have been great to meet many people in Edinburgh, but hopefully we'll get back to that soon.
Yeah, absolutely. Yeah. Well, who knows? Maybe at Data Summit next year we might be able to get the simulator up or something like that.
That'd be cool, yeah.
Have a good go at it.
Yeah, absolutely. And I appreciate everyone listening, and even though we've ran over time and stuff, so hopefully it was interesting.
No, I think from the amount of attendees that are still online, it definitely was interesting. I think everyone has really enjoyed it. And thanks everyone for joining in the question. Yeah, Gordon's here saying brilliant talk, very interesting. Thanks for all the questions that have come through.
Yeah, absolutely.
And
great.
Thanks to everyone who's joined it. And just, I guess, a bit of housekeeping for all the members. Like, we're going to try and do this as much as we can over the next while. If you want to get involved and maybe talk, if you have a suggestion for someone, we're open to. It's all a testing for us as well. So yeah, keep in touch, and we'll see everyone at the next one. So yeah, everyone just saying thanks there, Colin, to you. So
yeah, absolutely.
That's great. Great to see you. Thanks again, everyone.
Cheers. Appreciate it, everyone.
And again, thanks, Colin. So we'll see you all soon.
Bye bye.